Hello everyone, welcome to the recitation on homework workflows. Today we'll specifically cover the workflow for the part 2 of homework 1, 2 and 3. The workflow for the part 1 is comprehensively addressed in each of its corresponding write-ups. In this notebook, I'll be demonstrating the training of a basic MNIST classification network using PyTorch. So let us begin by installing and importing the necessary packages. So following this step, let us create our datasets. We are utilizing the MNIST dataset which is available within PyTorch datasets, specifically in Torch Vision. I'll proceed to download both the train set and the test set. As a standard practice, we will further split the train set to create validation set. So validation set would be 20% and then the actual training set would be 80%. Now let us create our data loader. Data loader feeds training data into neural networks in batches. When creating them, we need to specify the data set and batch size. Batch size here is a hyperparameter. So a size of 64 is used here, but larger sizes are possible with sufficient memory. It is crucial to shuffle the training set so that the model sees diverse data, while validation and test sets shouldn't be shuffled. Now, let us visualize the dataset. Our dataset primarily consists of digits. So the objective is to construct a neural network which is capable of accurately recognizing these digits. For instance, when presented with an input image depicting the digit 8, the network should successfully identify it. So let us also observe the data shape. So here 64 represents the batch size. 1 is indicative of the grayscale nature of our images, each of which is sized 28 cross 28 pixels. Now let us build a basic network to classify handwritten digits. So the input image here is 28 cross 28 pixels, which is flattened into a 1D vector of length 28 into 28 to feed into the multi-layer perceptron model. We use a hidden layer of size 1024 units, and we are making use of ReLU as the activation function. So the output layer is of size 10, 1 node per digit class. So while simple, this architecture is fully customizable. You can definitely experiment with more number of layers, different hidden sizes, and other activation functions. Now let us look at the optimizer and loss function. So here we are making use of Adam as the optimizer, and for our task, we are using cross entropy as the loss function. Please don't worry too much about the optimizers. You can choose any optimizer to begin with. And the choice of the loss function depends on the task, but for classification, cross entropy is most commonly used. Now let us create a helper function for both training and evaluating the model. So the train epoch function takes the model, optimizer, criterion, and data loader as inputs. It starts by setting the model to training mode to signal PyTorch that training is about to commence. So during training, it accumulates the training loss and maintains list for true and predicted labels. So as we iterate through the data loader, it sends images and labels to the device. So the images are flattened before being fed into the model as our multi-layer perceptron expects a one-dimensional input. So the function then calculates the loss between the model's output and the true labels, updating the training loss and accumulating the predicted labels. So this function will turn the train loss and train accuracy. So the eval function mirrors the structure of the train epoch function. However, it is essential to ensure that the model is in evaluation mode to prevent issues like unintended gradient overrides. While this may not trigger errors, it can definitely impact the model performance. So this function also returns the evaluation and loss accuracy. Now, with the help of these helper functions, we can train the model, and let us train the model for around 15 epochs, and also let us print the train loss, train accuracy, val loss, and val accuracy. So, as seen, we have already trained the model for 15 epochs.
Okay, so now we're done with the training and evaluation. But to better understand how our network is performing, let's visualize the data we have. We'll visualize the training and validation loss along with the training and validation accuracies. You can see that our network is overfitting, and there are a few reasons for that. One common reason is our data set, and other is that we've not performed any augmentations on our data as well. So to improve our model, we can add augmentations, add more data to the data set. We know it's overfitting because the training accuracy is increasing, but validation is not increasing. Now that we have visualized our data, let's move on to testing our data. In this case, we should improve our model and test it, but for demonstration purposes, we'll test it here. We test our model on a on the given on the test data set, and we see the test loss and accuracy accordingly. Now, by going through these various steps, we've seen the different stages of a deep learning project from start to finish. But feel free to experiment and change things. There is no such thing as one model or one approach is the best or which will work for everything. So you need to try different optimizers, architectures, hyperparameters, perform various experimentations and ablations. And hence, we provide an exercise for helping you understand better. Now, for the exercise, try increasing the layers of the network, changing its architecture, see how it affects the performance and what is improving the performance or what is not working. Also, explore different augmentation functions in the Python image augmentation library with the links given here, and try to incorporate them into the model. Augmentation, if done right, can help enhance performance a lot. So with that, we come to the end of this recitation. And if you have any questions, feel free to reach out. And all the best for your semester.